Hello, Matthews Gatos here. In this video, we're going to look at how do we graph linear rational functions. Rational functions meaning fractions, linear where the numerator and denominator are linear functions. So let's get started. In this first question, I want to graph and label the graph of y equals 2x minus 3 over x plus 2. So I do this in stages. The first thing that I'm going to do is look at the restrictions, which is division by 0. I can't divide by 0. So whatever my denominator is, it can't equal 0. So to isolate for x, I subtract 2 from both sides, and x can't equal 0. Take away 2 is negative 2. So that tells me I have a vertical asymptote at negative 2, and I'll just label that x equals negative 2. Vertical asymptote is an imaginary line on the graph that the graph cannot touch or cross, but it gets really close to it. Okay, second place I'm going to go to is my x-intercept. So to find an x-intercept, I know that I let y equal 0 and I solve for x. So to solve for x, I would just multiply both sides by x plus 2 to get rid of the denominator. 0 times x plus 2 is 0. And you can see a little shortcut there. You just set the numerator equal to 0. So I will add 3 to both sides, divide both sides by 2. So I get 3 over 2, which is 1.5. So I'll label that as well. Okay, so I have my vertical asymptote and I have my x-intercept. Next place I'll go to is my y-intercept. To find my y-intercept, I let x equal to 0 and solve for y. So if I let x equal to 0, I would have 2 times 0, which is 0, minus 3 over 0 plus 2. So my y-intercept is negative 3 over 2. So negative 1.5. So we'll call that right there, negative 3 over 2. Okay, next thing that I will look at is a horizontal asymptote. So what a horizontal asymptote is where the ends of the graph go. So imagine I make x a really, really, really big number. I want to know where the ends of my graph is going to go. So if I make a really, really big number of x and I times it by 2, it's going to be even bigger. When I subtract 3, that really doesn't have very much of an impact on a big, big number. So I divide it by x, which is my really big number, plus 2. Again, plus 2 doesn't really have much impact. So what I really have when it comes down to it is that my numerator is pretty much double my denominator. So I know that my horizontal asymptote is 2. That means the ends of my graph are going to approach y equal to 2. Okay, so I have a graph that is split into 4 different sections. So looking at that, I know that linear rational functions have mirror images of one another. So I know if I have a graph in this section, I'm going to have a graph in this section. They are opposite of one another. So I know I will not have a graph here, and I will not have a graph here. So what I do is I use what I know about asymptotes. The ends of the graph are attracted to the asymptotes. So they want to go really, really close to it, but they can't cross it or touch it. So I know in this section here, I'm going to pass through these 2 points, and the ends of my graph want to go towards the horizontal asymptote, and here the end of the graph wants to go towards the vertical asymptote. So it's going to look something like that. And then in the top section here, again, I'm going to be attracted at my ends to my vertical asymptote. I'm going to have to curve around to get my horizontal asymptote. So that would be a rough sketch of what it looks like. Again, you can always put that into the graphing calculator to check to see if your graph is accurate. Okay, let's look at number 2. Number 2 is write the equation of the function. So I have my function. I want to write the equation in transformed notation. So this all comes back to my base function. I know that my base function has a vertical asymptote at 0 and a horizontal asymptote at 0. So looking at this graph, I can see that my vertical asymptote becomes x equal to 1. The way that that happens is that I have moved 1 unit to the right. If I move 1 unit to the right, that means h has a value of 1. Now my horizontal asymptote used to be at 0. It has now moved to y equals to 2, which means I have a vertical translation 2 units up, which means my k value is 2. Now remember, with every graph that we do, we always solve for our vertical stretch or our a value. So I have my h and I have my k value. I'm going to use any other point that the graph passes through to solve for a. So for example, this y-intercept, I can use x is 0, y is -2. So putting it all together, I have y equals a over x minus h plus k, which is 2. So let's tidy this up a bit. 0 take away 1 is -1 plus 2. So now I'm just trying to isolate for my a value. So a divided by -1 is -a plus 2. I will subtract 2 from both sides and then divide both sides by -1. So a is equal to 4. So putting it all together, I have y equals to 4 over x minus 1 plus my k value of 2. That would be my equation. Again, I could put that into my calculator, see if it matches the graph that I started with. Okay, question number 3. I want to use long division to write this fraction, linear fraction form, into a transformed form. Why would I want to do that? The only benefit of going from fraction form to transformed form is so I can identify what my vertical stretch is, because I can't tell that in the fraction form. I can figure out my horizontal and vertical translation based on asymptotes, but I don't know what my vertical stretch is. So that's where long division comes in handy. So if I want to do 5x minus 6 divided by x plus 7, x plus 7 goes on the outside. That's the divisor. And I want to know how many groups of x plus 7 there are in 5x minus 6. So what I do is I just start with my x's. How many groups of x are there in 5x? Well, you can look at it that way, or say 5x divided by x is 5. So I put a 5 as the quotient, and then I do 5 times x, 5x, those should match. 5 times 7 is 35, and then I subtract. So 5x take away 5x is 0, it's gone. -6 take away 35 is -41. So what I want to do is write my division statement. So 5x minus 6 divided by x plus 7 is equal to 5 plus the remainder, -41, out of the divisor. So this means it goes in there 5 times with a remainder of -41. The remainder is always out of the divisor. So I can just flip that around and write it as -41 over x plus 7 plus 5. Now that it's in transformed notation, I can see, since a is -41, there has been a vertical reflection and a vertical stretch. I can also see plus 7, that there's been a horizontal translation and a vertical translation as well. That's the benefit of writing it in transformed form. Sometimes we want to go the other way around. In this last example that I have a function that's in transformed notation, and I want to know the domain and range. Now I can leave it in transformed form, or I could write it in fraction form. So I have y minus 3 equals -5 over x minus 2. So I'm going to add 3 to both sides, and I get y is equal to -5 x minus 2 plus 3. Now I could write this in fraction form, or I could leave it in transformed form. Just to practice, let's write it in fraction form. So to write it in fraction form, I need a common denominator, and that common denominator is x minus 2. So this is like 3 over 1. So I can see, to change this into an equivalent fraction, I need to multiply numerator and denominator by x minus 2. If I were to cancel those, I'd end up back where I started with 3, so I know I've created an equivalent fraction. So let's continue this on. I have y equals -5 over x minus 2 plus 3x minus 6 over x minus 2, which all together, let's write this as one big fraction out of x minus 2, is 3x, -5 and -6 is -11. Okay, so no matter which form I look at, I can see here that my denominator has a restriction of 2, which I could also see up here. My denominator has a restriction of 2. Here I can see that the -11 and -2 are really not important as I get x really, really big. I want to look where my ends of my graph are. I can see that the numerator is almost triple the denominator. So because of that, I know that I have a horizontal asymptote at 3. I can see that in my fraction form right here. So you can see in both forms, we can see what the vertical and horizontal asymptotes are. Now, the reason I wanted to do that is because we're finding domain and range. So again, it all comes back to your base function. Your base function has a vertical asymptote at 0 and a horizontal asymptote at 0 as well. So my new domain and range are going to be what my new vertical and horizontal asymptote are, because I've moved 2 to the right and 3 up. So my new domain is that x cannot equal to, the value is 2, so m is 2. And the value of n, because the range is y cannot equal to, and y cannot equal to 3. So I know that n is 3. So this question here talked about going from transformed form to fraction form, just so that I could find out my domain and range. So I hope that this video helped. If it did, please give it a thumbs up and hit subscribe so I can help more mathies just like you. Thanks for watching, and I'll see you for the next one.